So we're talking about physics today, um, demonstrating Wolfram language as a tool for physics research and teaching. I have a physics background myself. I studied astrophysics at university, which is where I was first introduced to Wolfram language, and um, I was able to use it for some of the modules that I did at the university, computational physics, and then one module in condensed matter. I could complete my homework solutions in Mathematica, which was great, and I could just upload the notebook. So this is kind of the part of the theme of this talk is using Wolfram products in your research and teaching, like I was able to do. Uh, I am going through quite a few examples which we have kind of curated and we believe fit into three categories. Either we're demonstrating the Wolfram language as complete, automated, or integrated. So we believe this is quite important. If you're going to have a tool that you use for physics computation, it should be all of these things. Okay, so the first example, we're going to demonstrate a example of um, the Wolfram language as a complete platform. So this this just gives a quite a few use cases of computation within physics. Okay, um, if you happen to work or study in any of these fields, whilst they might seem quite separate, there is probably some amount of computation that underlies all of them. Okay, so you can you can start to build um, computational tools that allow you to conduct further study into these areas, and we can say that this fits under the wider umbrella of physics computation. And if it's in this list, it likely is supported by the Wolfram language. So there'll be some functions that relate to all of these fields. So the first example, we're going to look at some gravity maps of Mars, I believe. For those of you who are familiar with Wolfram may know of Wolfram Alpha, a kind of computational search engine that has all of this built-in curated data on various scientific and other topics. Um, so we have all of this data from Wolfram Alpha. We also have access to what's called the Wolfram data repository. You can click this link in here. It will take you to the data repository. This is what it looks like, where we can search by category or by content type. And as you can see, we've got data for all of these different categories and even different content types as well. So it's not just rows and columns. It might be a vector database, a video, uh, text, audio, that kind of thing. So we'll just pick one of these at random. Physical sciences. Um, Here we go. Some jet wind profiles measured at night in the Arizona desert using a high dynamic range. Interesting. Okay, so this looks like some image analysis, but it's quite multi paradigm data source here, and well, because of the nature of Wolfram language, in that it treats most data as the same, this multi paradigm approach is not a problem. But let's leave this and get back to our example. So we're going to use this function resource object to get this specific resource object, which is the Goddard Mars Model 3 map of the gravity field of Mars. Okay, if you've ever seen something similar to like this of the Earth, I believe it's called a geoid, um, where you can see the varying gravitational field strength over the surface of the Earth. It's greater where you have perhaps like more massive rock or something like that. Yeah, so we're going to do a similar thing with Mars here. So we've got this object. We can query it for its properties. I'm just going to have to zoom out to fit these in. I will zoom back in. But yeah, so these are all of the properties kind of baked inside this resource object. Um, Taking one of these, we'll say we want to know its format, and then we have an association, which is a bit like a Python dictionary of key to value. So these things are formatted in PNG. Yeah, everything's a PNG basically. So as you can see, we have a gravity map, a crystal thickness map, uh, free air gravity, and MOLA elevation. MOLA, I believe, is the name of an instrument that was used to get this elevation. But yeah, this gives you a hint of what we're going to get out of this. Anyway, so the first thing we're going to do is get the gravity map. So this comes as a PNG, as we just saw, by querying for the format, and we're going to use the image resize function just to kind of um, format the size of the image. Okay, so there we are. We don't have the color function here, but mainly I just want to show how there's deviations. There's anisotropies in the gravitational field strength of Mars. Okay, and then we can take the elevation map. I'm very confident that the A in MOLA stands for altimeter, but I'm not sure about the rest. So let's take a look at what this looks like. Okay, so maybe you have some mountains on Mars. You know, Olympus Mons comes to mind. I think it's like just under double the height of Everest. Um, yes, and obviously this is a spherical surface projected onto 2D. So we are seeing the whole surface of Mars here, I would have thought. Uh, and then finally, the crystal thickness map. So I'm not entirely sure the instrument that you used to get the crystal thickness, some kind of penetrating radar, perhaps. But there we are. You might start to see some patterns between these three images. Okay, some regions of interest, let's say. Okay, so we've got our three images. Now, combining the maps, what does that really mean? I suppose what comes to mind is that when you have, let's say, a map, you're going on a hike or something like that, you see contour lines which show you the elevation. They show you where it's steeper or where it's shallow. Uh, so sometimes you want to kind of stack images on top of one another and see the result, because you have these two different things, but combining them would give you something a lot more useful than their constituent parts. So that's what we're going to do here. If you notice, this is just the same as this. So we could have easily just defined this as some variable and then do one variable minus the other. But we're going to just do a simple subtraction. This is akin in full form, if we're being quite strict with our use of the Wolfram language here. We're essentially doing subtract of A and B. But these are our images. Okay, so let's see what we get for that. You might be wondering, like, what does it mean to subtract one image from the other? Well, because of the way Wolfram language functions hold and handle data like this, it's kind of agnostic to the input. So it takes the pixel value at every point, at every pixel. So in this image, it takes the pixel value at every pixel and subtracts that from the pixel value at every pixel of this. Okay, it's a bit like just kind of having two lists here and subtracting one list from another list. Okay, so obviously the difference between 4 and 1 is 3, 5 and 2 is 3, 6 and 3 is 3, and we have a list of threes. Okay, so hopefully that was quite informative. It's a nice look at the data that's readily available to us, and also a reminder of kind of the agnostic nature of functions in Wolfram language. Okay, Arif has asked a question in Big Marker. Thank you very much. So he asks, by using all the data and knowledge base that Wolfram platform has, can we build an app that identifies a location or house and tells us how risky is the house for things like climate change and flooding and fires? Okay, great question. Um, yes, this is possible. I mean, I'd like you to stay to the end because I've been meaning to show these things that are on Wolfram Community. So it's a place where we can publish blog posts and things like that. And there's quite a frequent poster on there who has a whole package of functions relating to Earth observation data. Yeah, so naturally, if you have a question in mind, you have like a research question, can I do this with Wolfram language? Um, Instead of trying to do the whole thing yourself, there might be people who have paved the way for you in the form of creating this functionality, creating like database connectivity that you can just then use. Excellent. All right. I'm interested to see what you use that for, Arif. Next example, we've got some image processing. Okay, whilst it's not the first thing you think of when it comes to physics, I have certainly heard of companies in my capacity as a consultant that are interested in kind of automating their image processing. Okay, they're spending lots of time doing things manually, and if you're just checking for something that you could essentially train a machine to look for, um, you would save a lot of money and time. So the problem statement here is that we have some nanoparticles suspended in a gel. I believe this is some kind of injection into a membrane of sorts, and we want to see how the nanoparticles disperse through into this membrane. So this is an image of that, like a couple of some moments of time after that injection happens, and we'll just define this as an image. Um, we can use the image processing functions in Wolfram language to actually transform this image data into something that we can compute with. Okay, because it's not immediately obvious um, what you do here, at least with this image as it exists right now. Okay, but if we clean it up a bit and perform some image processing on it, then it transforms it into a much more computable form. So I'm going to run this function and just take you through some of the functions I used to get this. So this first tab here in this tab view is just two of the nanoparticles here, um, essentially just a cropped picture of two of them. And then we use delete small components and binarize to essentially clean the image. Okay, binarize transforms gray pixels to either black or white, um, depending on some threshold. I believe that when you give no threshold, a threshold is automatically picked for you. And then we delete the small components. So things like this we don't really care about. They get deleted. Okay. This next one is a bit more involved. it computes what's called a distance transform, which is some function of the pixels and their relationship to the background. Okay, uh, feel free to read the documentation for a bit more of an in-depth look at this, but yes, it's known as a distance transform. Okay, so now we've got this. If you really just care about the centroid or the center of these nanoparticles, you can just take the max of this um, transformed image, and then you just get two individual pixels representing the maxima. Okay, so the the workflow then is to do this for every one of these particles. Instead of this, we would just essentially paste the whole image into here, and this is what we're showing here. So we find these maxima and mark them on the image with a red cross. Okay, and then really the data that we're interested in is just the positions of these red crosses, which uh, which is just a list of XY pairs. Okay, and what can you do with a list of XY pairs? You can plot the distribution on a 3D histogram. Okay, so that's what we're going to do here. This is the result. We can move it around, try and make some sense of this in the context of this diagram. And what I'm seeing really is a kind of bimodal distribution, showing like the dense regions here, here, and kind of like an underdense region here. So I think this is quite a nice example. So we're still on complete examples. I believe this is the last one. I'm going to make this slightly bigger again. So a very important aspect of physics is being able to solve partial differential equations. Something that we have in Wolfram Language that's incredibly useful and has been worked on for many years and increasingly so in the latest version releases is a kind of unified approach to constructing partial differential equations across a range of fields. Okay, so before we actually go into the example, I'm just going to do a little function search of PDE component, because it gives you an idea of the functions that we have and the fields for which we support partial differential equation construction. Okay, so see if you recognize something here. Acoustic PDE component, electric current, electrostatic, fluid flow. You've got, Navier-Stokes equations involved there. Heat transfer, magnetic, magnetostatic, Schrodinger. Yeah, so all of these fields, right, really important in all of these areas of physics. And we're going to go through a solid mechanics example, uh, which outlines how you go about using functions like this. Okay, so these are very high level functions, and um, they are doing lots of the work for you behind the scenes, but I don't think it's at the expense of any understanding. So, what are we interested in doing? We have we're going to pretend we have a teaspoon with a force applied to it at a given point in space, and we're going to model the kind of deformation of this teaspoon subject to that force. So how do we do this, right? A differential equation needs variables and parameters. And we're going to define some variables, u, v, and w, that are the displacements in the x, y, and z direction. Okay, so these are all functions of x, y, and z, and obviously we have the variables x, y, and z as well, because we're in 3D space. Okay, the parameters is an association where the material goes to the entity that is silver. So if I hover over this, you can see a little gray box comes up and it says entity element silver. And these Wolfram language entities are a really powerful thing. So there's lots of information again baked into this, everything you could think of that you wanted to know about silver. Um, okay, so get its group. I could even ask for a boiling point, and I get a kind of autocorrect. Um, okay, very warm. So yeah, this is really nice because we can just specify that the material goes to silver. We don't even need to kind of extract all of these things, piece of information about silver. We can just say that the material goes to this entity that represents silver. Um, any questions about entities? I'm happy to answer too. So we need the domain over which we're going to solve the PDE. So we're going to import this .wxf file of a spoon. So you should all have access to this too. Okay. Now, let's look at this piece of code. So ND solve value is doing the solving of the partial differential equation, but I'm more interested in what's inside here. So we're going to use solid mechanics PDE component of our variables and parameters, which are defined here. And if you remember, solid mechanics was one of these that we saw earlier. Okay. Then we need to specify some actual conditions. Okay, what's going on in this solid mechanics problem? The way we do that is we say we have a solid boundary load value at x is greater than 1/10. And we even have an association saying what the force is. So the force is minus 100 newtons in the z direction. Okay. And then we also have a solid fixed condition for x is less than or equal to minus 1/10. Okay. The equation, this double equal sign here, is setting this equal to this. So this is essentially the thing that is solved, but this is also an equation. It's just not as obvious because it's the equation is kind of happening inside that solid fixed condition. So hopefully you understand the setup of this problem. Okay, then we just need to specify the variables we want to solve for, so u, v, and w, and the domain over which we want to solve, where x, y, and z are elements of the spoon model. All right. And this is something I evaluated before. So this is our result. We have interpolating functions of x, y, and z representing u, v, and w. So this is very nice. We see how each well, every point on the spoon model deforms because every point on the spoon model is some point x, y, z, and we essentially find out its x displacement, y displacement, and z displacement. So what would be useful here is to show this displacement visually, and we can do that with vector displacement plot 3D. Okay, so let's have a look at what we get here. This is showing the original spoon and the deformed spoon on the same diagram. So this kind of is consistent with the idea that a downwards force of 100 newtons was placed upon this this spoon. Great, and there we go. Quite a complicated workflow if you were to kind of take out a blackboard and solve these questions by hand, but these kind of PDE constructor kits really simplify things. And this is the result. Yeah, if you are concerned that this almost seems too easy and there's like some understanding going amiss here, then I'd encourage you to look at our tech notes on this topic. So we'll go to the documentation of solid mechanics PDE component here. So we can see some other use cases. But we have some tech notes here. So go into the tech note for solid mechanics, and it gives you more of a kind of comprehensive overview of how to solve these problems and the real physics behind them. Okay, so these are really good. It's a good resource. And we have these for all of the topics, so fluid flow, Schrodinger equation, that kind of thing. You even go into the PDE models overview, and we have all of them here. So fluid dynamics, PDEs, and boundary conditions. A guide is a bit different from a tech note. So a guide will just kind of is a kind of centralized place of where all the functions live. So fluid flow PD component, and then you have links to all of these examples. Uh, but yes, the tech note is more comprehensive. Great. There you go. Are there facilities in Wolfram for conformal mapping, specifically Schwarz-Christoffel transformation? Okay, this I'm afraid I don't know. Um, when I don't know, and I'm live, I I I feel like I should um, consult Wolfram Alpha and just see what it has to say about conformal mapping. Okay, so interesting. I didn't know this was a entity type, but um, it turns out there's an entity type for MathWorld term, and MathWorld is another website that yeah is operated by us at Wolfram, where all of these mathematics terms are defined. So let's see what we've got here. Basic definitions of conformal mapping. So this is a good sign for you, Ernst. I think that we have the makings of some support for this conformal mapping. I'm sure we do. We could even query the property related Wolfram language symbols. How about that? I really like it when I get questions like this, and it pays off. So thank you very much. Okay, so spoke too soon. So it hasn't found any related Wolfram language symbols there, but maybe I could go to the URL and then it might provide me with some better resources. So let's just open it up. So here's our Wolfram Math World page on conformal mapping. And yes, I mean, straight away, these plots will more, well, it's very likely they would have been made in Wolfram. So that's yes, you can download even the Wolfram notebook corresponding to this page. So I'm sure there's lots of support for this. And a very comprehensive list of references too. This is great. I should use MathWorld more. Um, okay, yeah. There we can. Oh, there's the one you even said. There's a MathWorld entry for the exact kind of mapping you talked about, Schwarz-Christoffel. Partha has asked, what are these data types highlighted in yellow called? Good question. These are called entities. Um, so let me. So this is the kind of a wrapper for this data type, or this object, let's say. So entity of a certain type with a certain name represents an entity of the specified type identified by name. Okay. Um, Documentation page is good for this because it'll start you off with some basic examples like countries that you can query by population. Um, Planets, for example, cities. Yes. I believe you can even define your own entities for your own use. Uh, but yes, if it looks like this kind of orange box, it's an entity. So it belongs to some entity class, in this case, math world term. Okay. And just like before, silver belonged to the entity that was an element or the entity class of elements. One of my favorites is Wolfram language symbols that are entities themselves. So I think this will work. Yes. So plot is obviously a very common Wolfram language function. And inside, well, we have our own entity framework for Wolfram language functions themselves. So we can um, find some properties of this. And this is quite meta because you're um, evaluating Wolfram language functions on entities representing Wolfram language functions. And you can find out, the date it was introduced, the date it was modified. URL, I believe that's just a link to the online documentation. So I'm going to ask for the versions plot was modified. As you can see, it's quite a lot of them. Just to show off a new function, we have tabular, and I could show that this was introduced in version 14.2. So there you go. That's a rapid course introduction to entities. Okay. Now we move on to showing the automated nature of Wolfram language. Okay, the benefits that it gives you in the sense that it automates trivial tasks, and also kind of feeds into this declarative nature of what you want to do um, when you compute something. You don't necessarily want to give the computer all of the steps to accomplish something. You're more declarative about it. So I'll go through this example that explains what I mean. So often in astronomy, you might want to classify objects, whether that's supernovae or galaxies or planets, stars, that kind of thing. And these objects often have particular attributes that differentiate them from other objects. Okay, so galaxies, for example, can often be grouped into either the spiral category or the elliptical category. So we have some examples of spiral galaxies here where there are lots of star-forming regions. They give off a bluer light. Um, they have these nice spiral arms. And we have elliptical galaxies, they tend to be older. They give off a redder light, and it's unlikely that there's any star forming going on in those. They're often described as actually red and dead. Yeah, so obviously these look quite different. And if you had some, I don't know, James Webb Space Telescope data for these, you would have much more data than just a picture to distinguish them, and maybe you'd want to build a quite technical classifier to say, okay, I have 100 features on each of these galaxies. Um, can these features tell me which group it goes in? Okay, so we're going to do a very rudimentary version of that by just looking at the pictures. using the Wolfram Language super function classify. Okay, so what this does is it creates a machine learning model that classifies images into either spiral or elliptical galaxies. Okay, this is our training data. It is labeled, so we're doing supervised learning here. Um, so it knows that there are only two categories possible. So let's run this and look out for what comes up. Okay, so that was so quick that you couldn't really see what's going on there. So I might just increase the time goal to 20 seconds and do this again. So as you can see, it's got a current best method of classification. Um, as it goes through the training examples, it's essentially validating the method that it's chosen. But we didn't specify a method, so this is a kind of automated method choosing algorithm that's happening. It's algorithms on algorithms. Okay, it's uh, there's an algorithm which automates the process of which algorithm to choose to classify these images. Um, yes, and all we had to use was this function classify. So there's a lot going on behind the scenes here. But if you're not a machine learning expert, this is exactly what you need. Okay, so the only way to test if a model is any good is to apply it to unseen images. So here we're going to use this function map um, and map our classifier over these images to see what it classifies them as. Okay, so it's classified this one as spiral, elliptical, spiral, elliptical, spiral, elliptical. So I think it's done a pretty good job there. So this is nice. It's not a, it's not a very exhaustive example by any means, but it gives you an idea of what's possible um, using these high level declarative Wolfram language functions. Okay. The next example we have another differential equation. This time uh, it's a first order approximation to the velocity of a rocket. Okay, where this takes into account the mass of the rocket and all of the fuel that it's transporting. Some of you may be familiar with the kind of classic problem when it comes to rockets of the sheer amount of fuel you need to lift off increases the mass. So you need more fuel, which increases the mass. So you need more fuel, etc., etc. So we have some data in a .dat file, which is some time velocity pairs as this rocket is launched. So I can import that. Here we go. From 2 seconds to 60 seconds, I believe. So it's like the 0 to 60 speed of a rocket, which is quite funny. Yeah, okay. So we're going to try and fit a model to this data. Um, so we're going to assume that there is no symbolic solution available, and also assume that we're confident in our estimates for all parameter values except for beta. And this is the fuel consumption in kilograms per second. So when you're fitting a model to some data, often that gives you a best estimate value for one of the parameters, in our case, beta. So we're going to take this kind of typeset form and convert it to a form that we can use with our solving functions. So we have the first time derivative of v is equal to beta ve over this denominator minus g, where we have an initial condition that at 0 time the velocity is 0. And then we use a replace all to set these values. So I guess we have a mass of 10,000 kilograms. Yeah, it's just specified here. Okay, so we've got the equations list, and then we just give that equations list to parametric ND solve. Again, this is a numeric differential equation solver where we want to solve for v. We want the velocity. We have a domain, just like we had a domain that was the spoon before, but this time our domain is the times from 0 to 60, and we have a free parameter that is beta. Just checking that it solved these. Yeah. So here's our solution for v. We have v goes to some parametric function where beta is still a free parameter, by the way. We haven't fitted any data to this, so we still don't know what beta is. This is where nonlinear model fit comes in. So for nonlinear model fit, all we have to do is give it our data, give it the form of the form of the fit that we want, which in this case is our v. That's a function of beta and t. And then we can run this. We have our fitted model. We also have linear model fits. For example, if you just, you're fitting a straight line to some data, that is just called linear model fit. Okay, very similar, just for linear models. There's also lots of functions in the function repository that are kind of continuations of this. So you can fit a linear or nonlinear model to data with error bars, for example. That's very useful, but the mathematics is quite hard. Okay, so we've got our rocket model. We can plot this from 0 to 60, and we can include the data on the plot as points. And we can see that we have some acceleration here, and it follows our data very nicely. Perhaps there should be some axes labels here. Okay, so now visually we're happy with our fit. But you might want to interrogate the fit a bit more and check the residuals or things like that, or actually find out find out the value of beta that was considered the best fit. So this by querying the parameter table, that's what we're going to find. So it found a beta of 149.804. We have some standard errors in this. We have the bias in our parameter and then ANOVA table as well. So these are all the kind of properties of this object fitted model that we can query. And then we can plot the residuals. Yeah. Yeah. I just wondered then why it only goes up to 30, but because there are 30 data points from 0 to 60, I think it's like every 2 seconds. Yeah. So if you wanted, you could play around with the x-axis here and kind of rescale it, so you're actually finding the residuals at the times. Amara has said, when I try to import the data, it fails. Can you provide the solution? So just check that you've downloaded all of the additional files, and there is some initialization cells at the end of the notebook. So I'm just going to show these here. This essentially sets your directory to the notebook directory and then goes into the additional files folder. So it tells it tells the kernel where to look, basically, for the file you're wanting to import. Hopefully that works. I can't think of what else it could be. Question from Abdel. How can we use Mathematica to analyze the surface chemical interaction? For example, we have a different species of cold plasma. This interacts with different surfaces for amazing chemical interaction. I mean, you may have just given me a perfect prompt for the notebook assistant later. So, um, yes, I'm not entirely sure how I go about your specific problem there, but I'm sure we have some functions that support this kind of chemical interaction and mathematical modeling. Um, but yeah, thanks for your question, and we might be able to come back to this. All right, so we're coming to the end of the examples. This last one is kind of a classic for most people who've done some kind of physics or astrophysics degree. At some point, you've probably seen an n-body simulation. Okay, I happened to make one using Fortran when I was at university, which wasn't even that long ago. So it's quite telling that they were still using Fortran. But let's look at how we can do this with Wolfram language. So we're going to say we want to simulate for 5 seconds with 5 bodies, and we're going to, I'll just look inside this function first. We're going to give all of these bodies a mass of 1, and we're going to set their positions and velocities to be random. Okay. Uh, Now let's look at this n-body simulation function. So all this needs is um, essentially a gravity law to specify. We're going to use the inverse square law, which is what we're all used to, um, and then some initial conditions and how long to simulate for. So we can just run this and we get a n-body simulation data object. And this essentially contains all of the paths of all of the bodies from t is 0 to t is t max. So we can show these using a parametric plot. So this evaluate is kind of just digging around in this data, getting all of the positions at all times t. And here we go. So this is the result. Obviously, you could add your own styling to this, but I'm quite keen to show this next part where we use a manipulate by just adding traces to each one of the bodies, and we can actually see how this evolves over time in an interactive way. This is very nice. Um, I'm keen to actually do a little experiment to see what other laws of gravity might give. So, I mean, got the documentation page up here. So we can also give an option. We can give law to be a inverse square, as we showed, harmonic, Newtonian, um, the Coulomb force. Yeah, I guess just simulating charges as well. Interesting. We can even query things like the total kinetic energy and uh, in the simulation, just like we did with the position. We can get the Hamiltonian equations for the system. Wow, this is brilliant. I haven't quite. Usually, I'm running out of time by this point, so I don't go into this as much. Um, but yeah, I'd encourage you to look at this further. Because this is random, we can just run it again, and we get a completely different um, set of interactions. This looks quite cool. We have the red and the green lines kind of pirouetting around one another a bit. So I'd be keen to see what this looks like. Yes. So, yeah, have a play around with this if you have access to the notebook. Another question saying, can it also be simulated in a rotating system with Coriolis forces? Good question. So, if you have like this is kind of combining like n-body simulation versus like the partial differential equation solving we saw earlier, perhaps. So, as long as you have expressions for those Coriolis forces, um, you should be able to incorporate them into a model like this. So, I actually just found a demonstrations project where it looks at the Coriolis force on the surface of the Earth. So this is quite cool. So yeah, you have a projectile launched at a fixed latitude on the surface of the Earth, um, and then we can kind of simulate the effect of the Coriolis force. So yeah, I'd take a look at this if you're interested. Paste the link in the chat in the Q&A. Rike asks, can one infer the initial conditions from the trajectories? Um, hmm, perhaps. Uh, perhaps you'd have to do some more of a detailed inquiry to find that. If there is a driving force, you could probably, infer what kind of law of gravity is operating based on any given simulation, and also the energies might give that away too. I don't think I can query the properties here, but I can. So I'm just trying to follow the example in the simulation and the documentation where we could query for the kinetic energy. Okay. Think you need to say that you want the kinetic energy at some time. Evaluate this. Hmm. I'll show you. I'll show again what I was trying to do, but perhaps I need to spend a bit more time looking at this. Um, in this example, in the documentation, we were able to um, show how the energy evolves during a simulation by plotting the total kinetic energy, total pairwise interaction energy, and the total energy as a function of time. Yeah, so if I just okay, so I can make this for my own simulation. That's quite nice. Um, yeah, so there's lots to do here. Uh, thank you everyone for your questions. So that was the last example, and this next section is really more about showing you um, more of the wider Wolfram ecosystem. Okay, I've hinted at the data repository, the function repository, um, Wolfram community demonstrations so far, but you'll find resources to all of these and examples in the coming slides. But yes, so hopefully you found these examples useful, and it was in a very small amount of code I was able to communicate like these ideas to all of you watching. Um, and when you're at university or in your job, you want to be able to communicate ideas clearly and quickly, right? Whether you're talking to your supervisor or your colleagues. So, in that sense, the goals of your research and the goals of your teaching and collaboration are quite similar. And that's what we've kind of concluded here. And we believe that Wolfram Language gives you the tools to um, essentially tick off all of these points. So let's look at some other things that you know Wolfram Language enables you to do. Wolfram Language, as well as using these computational notebooks. So I've actually done this whole presentation from a notebook. Um, as you can see, I'm in the presentation mode right now, but I could just go off this and um, go into a working screen environment, and you can see that this is just like a notebook, like any other notebook. Um, yes, and what comes along with that is that you can have code, text, graphics, um, all in the same place. And some more features here. We have like large language model integration. Um, you can deploy content straight to the cloud from the notebook. You can access Wolfram Alpha like I did before. Uh, and increasingly, we're seeing kind of textbooks being written with computation in mind. Okay. There are lots of books behind me, as you might be able to see. I just picked up one before. It's Mathematica in Theoretical Physics. So this was written a while ago, but it's got lots of examples of where people have used Mathematica, now called the Wolfram language, in theoretical physics. Okay, and there's some links to some other textbooks here as well. As you may have heard, we have AI assisted notebooks now. So um, you can go to your file, new, and then just open a chat notebook, and you have a chat cell here. So this, if you have, your notebook assistant LLM kit subscription, you can just type away here, or if you have the API key for your LLM of choice, you can also kind of communicate with that straight from the notebook. So um, this is at Wolfram. We had this early integration with ChatGPT, which meant people um, could kind of code in natural language like this, right? Now I have my manipulatable sign function with A and B. We can vary them. So this is quite a nice example. So that shows kind of interacting with LLMs in a free-form way, but we also have these LLM functions, which are a bit more of a programmatic way of interacting with LLMs. So it's a trivial example here, but I've got this string template, which is tell me an interesting fact about insert person here, and I've given it an association that person goes to Albert Einstein. Okay, and then we have a interesting fact here. I could also be a bit, stricter about my definition, define it here as a function, and then map this function over a list of of let's say famous scientists. And okay, so this function just works like any other function. Oh, I think I need. Audio. been a while since I looked at these. So, uh, but yeah, the point is that these LLM functions work like any other functions. You can map them over lists, etc. Um, okay. Um, what else have we got? Yeah, I mentioned Wolfram demonstrations before. This has got countless examples on all areas of physics. Here's a nice illustration of like the potential and the electric field between two charges. You can change the distance these are apart. You can change the sign of the charges, that kind of thing. Um, yeah, and there's more examples here. Yeah, and this is the just a point about Wolfram Alpha. So if you know how to program with Wolfram language, you might type out something like this in perfectly accurate Wolfram language code. You can also use formula lookup. If you didn't know the actual name, you could just maybe look up water hammer like this, and then you have these two options, and then you just take this and paste it into your formula data. But we could just use Wolfram Alpha. So the way you get these Wolfram Alpha cells is you open a new cell and press equals equals, and this is what's called a Wolfram Alpha long cell. So really, we're asking the same question here as here. It's just here we're asking it to Wolfram Alpha. You can see we get a very similar, if not the exact same formula. Okay, we could also ask it really complicated questions like this, and it will use the formulas it knows. In this case, a formula that works out gravitational time dilation. Yes, and you also have access to step-by-step solutions too. If I just click this step-by-step solution button, I mentioned before the usefulness of having code, text, and graphics all in the same place because it allows you to write what has been called a computational essay. Um, so there's lots of good examples of these on the Wolfram blog or on Stephen Wolfram's writings. This is one on the like random walk modeling of a drunken sailor that we have. I think you have access to this in the additional files. So yeah, that brings us to the end of the main part of the talk, where the examples illustrated Wolfram language as complete, highly automated, and integrated. And then we also went into some of the broader parts of the Wolfram ecosystem at the end, um, showing you that there's lots out there for physics research and teaching.